7.3 notes logarithmic functions. We will be seeing the word logarithmic reduced to just the word log. Okay? So this is definitely new. You haven't seen it before. So the inverse operation of an exponential equation, which is raising a base to an exponent. So our exponential equation was like ab to the power of x, is called finding the logarithm. A logarithm is the exponent to which a specified base is raised to obtain a given value. Okay, so a logarithm is going to help us find an unknown power. So you need to know these two forms, exponential equation, change to logarithm, but also how to change a logarithm to exponential equation. So first things first, b is your base for both the exponential equation and for the logarithmic equation. So this says log base b of a. That's how you read it. Log base b of a equals x. This is b to the x equals a. So b, the base of your exponent and the base of your log, has to be greater than 0. It can never be 0. It's never going to be negative. The base can also never be 1, though. So you can have a decimal between 0 and 1, and you can have a number greater than 1, but never less than 0, never 0, never 1. X and a, they can be anything, okay? So, but I need you to be able to transfer this. So the base of your exponent becomes the base of your log. The power on your exponential function is the answer to your log. So I'll say this again. Logs solve for unknown exponents. Logs solve for unknown exponents. That's the whole purpose of logarithms, is to help find an unknown exponent. All right, so logs solve for unknown exponents. So the base is the base, the power becomes the answer, and what you had as your answer is what you're taking the log of. You're trying to break it down. So we're going to do some converting. You should be comfortable with this converting formula. So you have 2 to the 6 equals 64. That is a true statement. Now, if I change it to logarithmic form, it is going to be the log base what? Well, the base of your exponent was 2, so log base 2 of 64 is the exponent of 6. So you could do this little loop. Log base 2 of 64 is 6. See how those little arrows twist around? So we all know 4 to the first is 4, right? Change this from exponential form to logarithmic form. So it's going to be log base what? 4 to the power of, log base 4 of 4 equals 1. So log base 4 of 4 is 1. All right, we know that anything to the power of 0 is always 1. So these are all true statements. Just change the form. This would be log base what? 5 of 1 equals 0. Now I'm going to put a star beside these two because these are special properties we're going to get to later. So those don't look really like stars, but they're supposed to be. Okay. So these are things that we're going to get to later. They are special properties of logarithms, just like they're special properties of powers. Okay, now this has a negative exponent. Just think about this. Exponentially, isn't this the same as 1 over 5 squared, which is 1 over 25? I mean, this is what we're used to, right? We have 5 to the negative power. A negative exponent would move it to the denominator, and 5 squared, there's your 1 over 25. If you type 1 over 25 in a calculator, you'll get 0.04. Not what we needed to do, but I wanted to make sure you remember why this negative exponent is giving us a small decimal. Now, take 5 as your base. So log base 5 of 0.04 is negative 2. So if your log is equal to a negative value, it's because you had a negative exponent. Now, this is a true exponential form. We don't know what x is. 3 to some power gives us 81. 3 to some power gives us 81. Well, do we know what that power is just by trying some numbers? 3 to the what? Well, it happens to be 4. 3 to the third is 27. Another 3 gives us that. We don't need to know that, but I could tell you that x is 4. But what if it was some weird number? What if this was 3 to some power gives me 90? It's not going to be a nice number. So we would change this to logarithmic form. Log base 3 of what? 81 equals x. So do you see how that log would find that unknown power? So we haven't solved anything. All we were practicing was changing exponential and logarithmic form. Okay, now let's reverse it. I'm giving you the logarithmic form. You give me the exponential form. So what's my base here? If you would read it, log base 10 of 100 equals 2. So your base is 10 to the power of 2 equals, do you see how the arrows work here? 10 to the second is 100. Well, that's a true statement, right? 10 squared is 100. All right, what's the next one? 7 to the is 49. So base is your base. Log solve for unknown exponents, so it becomes our exponent. All right, now this one would be 8 to the negative 1 equals 0.125. That makes sense because what is 1 or 8 to the negative 1? Isn't it 1 over 8, which is 0.125? We're going to need to understand these relationships. Okay, what about this one? Base is 5. What's the power? 5 to the first is 5. I'm going to put a star beside that because that's, again, a special property. And what about E? What's my base? 12 to the is 1. Okay. Now, so I'm going to throw these properties right here. If you look down, that's this property right here. Log base B of B will always be 1. If your log base is the same of what you're taking the log of, it cancels out and it gives you 1. Because if I have something to an unknown power, something to power 1, it's going to give me back itself. So they're showing you log base 10 of 10 is 1 because 10 to the first is 10. So if you forget the rule, you could always change it and catch, oh, that should be 1. And then this guy right here, anytime you have the log of 1, it doesn't matter what your base is, you will always get 0. The log of 1 will always give you 0 because anything to the power 0 is 1. So that's what's nice, is if you forget your rule, you can always use your change of form to sort of remember that power property. So these are power properties that we've known, we've worked with for years, we've talked about them this year. Now they're coming into play. So all your power properties are going to connect to all your log properties. Okay, now a logarithm with base 10 is called a common log. It is the most commonly used log. So a logarithm with the base 10 is called a common log. If no base is written for a logarithm, then the base is assumed to be a 10. So if I wrote you log 5, that is understood that it is log base 10 of 5. Okay, so if you just see log, then you understand it's base 10. That should remind you of this. This is the what root? That's a square root. Do we have to put the little 2 there? No, because it's like the common root. Okay, any other index we put in there. All right, so if you think about this, we have log of 1,000. What's the base here? 10. So I think it would help you if you rewrote it and put that piece in there. And it says equals a question mark. I'm going to go ahead and throw the idea of like, we could put a variable in there. So it says evaluate logarithms using mental math. So we're not typing this in the calculator at all. So this would be 10 to some power equals 1,000. Well, 10 times 10 is 100. 10 to the what? Well, okay, so this would be a variable. If we put an x there, but I'm asking what would fit in that. What could x be? 10 to the what gives me 1,000? Too big. 10 squared is 100. 10 to the third. So this is equal to 3. So I actually do prefer what you said. Like, I like to replace this with an x. So I'm going to write this as 4 to some power, right? 4 to the x equals 1/4. So now I have to think about this. I'm not using a calculator for this. That's the -1. That's why I was talking about that idea. What would make my 4 jump down to the denominator if my power was negative? So x for us is -1. That makes sense because 4 to the negative 1 is 1 over 4. So anytime you end up with a fraction or a decimal from a integer number, or I guess a whole number, you know that you are dealing with the negative exponent. Okay, now what's the base of number 3? It's assumed to be 10, and we're looking for what it equals. So this is 10 to some power equals 1, 2, 3, 4. 1, 2, 3, 4 zeros and then a 1. Okay, so did you get that my number got smaller? So I know my exponent must be negative. Now I just want you to rewrite this. How would I write this as a fraction? So 10th, 100th, 1000th, 10,000th, 100,000. So this would be 100,000. 100, or no, I think it should be, did I put too many decimals here? 10th, 100th, 1000th, 10,000th, 100,000th. Okay. So this would be, well, what would move my decimal 4 places? 1, 2, 3, 4, 5 places. Sorry.
So negative 100?
No. The power of 100 would be way too big. If you look at this, this would be negative 5 because that would move my decimal 1, 2, 3, 4, 5 places. Okay, so that would be my power would be negative 5. So that's a little tough, but taking it from a decimal and thinking about it as a fraction is helpful. Okay, look at number 4. This is equal to x, so my base is 25. What's my exponent? X, and it equals what? 0.04, which is 400. So let's take that 400ths and make it a fraction. Well, isn't 400ths the same as 4 over 100? Well, what's 4 over 100 reduced to? Oh, now that's a lot easier to think about, isn't it? I see that my value has moved to the denominator, but it stayed the same. So what would be my power? Negative 1. Okay, so you're going to have some to do with no calculator, meaning mental math. Okay, so because logarithms are inverses of exponents, the inverse of an exponential function is a logarithmic function. So y equals 2 to the x is equal to the logarithmic function. All right, now think about this. You know how we change the base to the power gives me that a value. What would be the inverse of y equals 2 to the x? Well, when we find inverse, what is it? No, it's not going to be log xy. When we find inverses, don't we switch the x and the y? So if you think about it, it's going to be log base 2 of x equals y. So if you would rewrite this to find the inverse, the first step to finding inverse was to switch x and y. Do you see what I did there? So 2 is my base, 2 to the power of x, sorry, 2 is my base, 2 to the y equals x. I'm backwards here. Let me rewrite it how we normally see it. Okay, here it goes. Log base 2 of x is y. So to find the inverse, we flipped x and y, but I'm going to take this and put it in logarithmic form. Okay, so we'll work with this. Just be comfortable changing from exponential form to logarithmic form. If I need the inverse, I've got to flip x and y, and then I'm using logarithms to solve for it. All right, so realize the domain and range are going to be switched just like before. So the domain of an exponential function is all real. So if you come down to your graph, you see this is y equals 2 to the x. It goes up, but to the right, it goes down, and it sort of hovers here to the left. So the domain is all reals, and the range is 0 to infinity, because remember, this is an asymptote here. So this won't go any lower than 0. You have an asymptote at y equals 0. Then if we reverse the domain and range, we will get the logarithmic inverse for this function. So now the domain of its inverse is the old range, and the range is the old domain. And this is that line y equals x. This is your line of reflection right here. So we can take this point and reflect it right to here. We can take this point and reflect it. And so everything reflects over here. So here is your exponential function, and here is its inverse logarithmic function. Okay, that's what it looks like. All right, next part is us doing it. Now, here's going to be the easy part. We're just going to type this in a calculator. 4 to the negative 2 is 1/16, because that's the same as 4 to the negative second, which is 1 over 4 squared. Same thing here. This is going to be 4 to the 0, which is 1. 4 to the first is 4, and 4 squared is 16. Let's graph these. Now, 1/16 is pretty close to 0. 1/4 is 0.25. All right, so graph this function, the original exponential function. All right, so negative 2 is a little bit off the graph here. So is negative 1. Remember, you're counting by halves here. All right, now we're getting on the graph. And now it's starting to jump. So there is my function, and it's going to stay right along that x-axis. Now, the easiest way to find the inverse would be to do what? Instead of plugging the values in here, can't I just take my function and flip it? 1/16 would give me negative 2. 1/4 would give me negative 1. 1, 0, 4, 1, 16, 2. We find inverses, we flip the x and y. And then we're going to graph that. So x is just there, and it's down here at negative 2. 1/4, negative 1. And then way out here to 16, 2. And there is my other function. And can you see that symmetry now? If we would fold this over, they would line up. So exponential is going to take off. Now this is exponential growth. If it was decay, it would be coming in. And this is my logarithm, my inverse. So you are seeing that exponential functions and logarithmic functions are inverses of each other. Okay, so you have one to try down here. First things first, if you want to use your calculator, you can. It might be easier if you think about these as decimals when you go to graph. So I know that I can deal with this because a negative power is going to flip it. And it's going to be 5 over 2 to the negative second, which makes it 2 over 5 to the second, which makes it 4 over 25. But I think I want the decimals to help me graph, so I'm going to go with my decimals. So take a second and you find these numbers. Okay, so we've got our decimals, we made our graph. I went ahead and labeled this f of x, even though it's color-coded. Now, the easy thing to do would be ignore this and just to flip your points, because we do know that this would make our inverse. We have to figure out what our inverse function is. So take a second and think about that as we transfer our points. So I can graph this without actually knowing what the inverse function is, just by using the original and then doing its points. Now, how do we find the inverse? Well, we take the original function, and the original function was y equals 5 over 2x. Bless you. Now, the way to find inverse is to flip x and y. Not the fraction, flip x and y. Now change this from exponential form to logarithmic form. So here's what I want you to think about. When we switched x and y, please, this is a big idea. This is like the difference between I get math and I'm getting by in math. We switched x and y was the first rule. The second rule to find inverses was to solve for y. Guys, there's no inverse operation like add, subtract, multiply, divide like we used before to get this power out of there. What do logarithms do? They solve for unknown exponents. I'm trying to solve for that unknown exponent. So I'm going to take this, instead of having to take the log both sides, I'm going to take it out of exponential form and put it in logarithmic form. So this is going to be log base what?
Log base 5 over 2.
Yeah, 5 over 2. So make sure that shows as a fraction. That's not very good right there. Of what? Log base 5 over 2 of x equals y. That's a really big idea. Now, we would replace that y with the function notation for an inverse, and that would be the inverse of the function x equals log of 5 over 2, log base 5 over 2 of x. Okay, now take a second and graph your inverse. So we've graphed it, we've got our inverse function, we see our line of symmetry at y equals x, thus the flipping the x and the y's. Okay with that? All right, last part. The most interesting part. Maybe you won't feel the same way, but I think it's interesting. And have you gotten to logarithms in chemistry yet?
No.
Well, fabulous. I like it when we're ahead of that. Okay.
Why are we doing moles and liters?
So a chemist regularly tests rain samples to determine the rain's acidity or concentration of hydrogen ions known as H+. Acidity is measured in pH. So we hear about pH. You know, people test their pools for the pH level. You talk about testing soil because different plants can grow in different pH levels. Foods, drinks have different pH levels. So the function for the pH is negative log of H+. Now, H+ stood for the concentration of hydrogen ions. Oh, it tells us that again. H+ represents the hydrogen ion concentration in moles per liter. Find the pH of rainwater from each location and round to the nearest hundredth. So I am doing nothing more than plugging this in to a formula. That's it. I don't have to understand moles per liter. I don't have to understand anything else. I just need to know the pH level. So you've got some places on the map here, and you can see the hydrogen ion concentration, and it definitely is bigger in eastern Ohio than it is in central North Dakota, and so you can compare. So let's talk about the hydrogen ion concentration in central New Jersey. I'm not expecting you to memorize this formula, but most of you will know it because we use it a couple times. So what is the pH level? It's going to be negative log, and then what is the hydrogen ion concentration? Right here. How many zeros? 1, 2, 3, 4. 1, 2, 3, 4. 316 moles per liter. I'm not asking you to do this by hand, so let's talk about where that logarithmic button is in your calculators. It says log. So if you turn on your little calculator and you look down the left-hand side right beside the 7, there's your log key. Now, you're going to type in your negative sign. Don't forget that. And then you just type in log. It understands it's going to be like -1 times log. And put your number in there. Watch your decimal places. No, I mean, the parentheses just pop up on it automatically. And then hit enter, and we have a pH level of 4.5. We'll round to the nearest, what do you call it? We'll go to the nearest hundredth, so 4.50. So pH equals 4.50. So it's a word problem. What does that really mean? pH level where? In central New Jersey, yep, is 4.50. All right, so you take a second and find me the pH level for central North Dakota. You're using that same formula. Write it down, though, even though you're using your calculator. So we are going to find the pH by plugging it into negative log, and then watch your 1, 2, 3, 4, 5, 6. Okay. Watch your zeros because that does make a big difference. And it doesn't, I use brackets, but you can use brackets or parentheses. It's just to group it. And then again, you're going to type in negative, then your log key right beside the 7. Count your zeros. And that is 6.05 if we round it. So pH equals 6.05. So we would say pH, or the pH level. pH level, I guess we'd be saying of rain, but of rainwater.
How much battery has that with pH level of 0?
Of rainwater is 6.05 in central North Dakota.